So in this video we're going to be processing our IR spectrum and correcting the baseline and labeling peaks and doing some searching to find out what functional groups are present and how we can tell those functional groups are present. So I'm going to go ahead and log into this computer using the chemistry 1114 password. We'll open up the OMNIC software, which is the same software we used to collect the spectrum. Which is the thermoscientific software on version 9. And starting from a blank window, we'll go to menu and open our spectrum, and that was stored on the student drive in the data folder under my name in 2020 Fall Lab, the trimyristin lab, and we've got this DCL-10-42B-1 spectrum which we can open. And you recall that the baseline was kind of sloped. High energy side on the left, there was a lot more light scattering, and so we didn't get a clean baseline. We kind of got this sloping baseline. One of the first things we're going to want to do is to set that baseline so that it's more flat. And there's a button in the top section where there are two here, which if I hover over it will tell you that's baseline correct. And I can click on that and it'll open a window, the baseline correct window. In the baseline correct window, we have on the top our spectrum, and on the bottom what the corrected spectrum will look like. So I can click anywhere on what I know to be the baseline and create a gray horizontal line. Anything on that gray horizontal line is now being set equal to 100% transmittance, which is the baseline. And you see the little gray box. Right? Anywhere I do a little gray box becomes baseline. So I can set another point over here by clicking on it, and then that gray box there is also baseline, and I can do the same here. And so I've told it that that whole section should be flat baseline. If I grab the gray box on the far left and pull it down until it's on the baseline, that, you'll see, corrects the baseline and makes it nice and flat over that entire region. And I can probably put a baseline point here, because that is also likely. This peak is water. It's not part of my spectrum, but I'm going to leave it there for now, and we'll have a different way of dealing. I also want to grab the gray box on the far right and drag it up so that I see my baseline, and then put a couple more points in here so I'm knocking off those peaks. So everywhere that the gray boxes is now assumed to be baseline. And when I have it looking the way I want it in this lower window in the blue spectrum, I can click the replace button here. And that will put the corrected copy. And you see now we have a nice flat baseline at 100% transmittance. Over there you can see it's 100% transmittance. Right? And a flat baseline all the way over to the right-hand side, from 400 to 4,000 wave numbers. So it's a nice baseline now. If the spectrum label is in the way, I can use the T down here. Right, there's an annotation tool, which looks like a T. And I can click on the tool and then click and drag, and I can pull that spectrum or that label anywhere I want. If I want to edit that, I can double click on the title bar and I can put in comments. So I could say, I know this is trimyristin from nutmeg. So that label can then be dragged anywhere I want by just clicking and pulling it somewhere that's out of the way, like the bottom corner. And then I can go back to the select tool down here in the menu. That's the selection tool, the one that looks like an arrow, and click on that, and that will get me back to the tool I need to continue working with the spectrum. Next thing I'm going to want to do is label peaks. Right? We definitely want to label the 4 peaks that are in this region and these strong peaks here. And I probably want to have my percent transmittance scale set not at 65 here, but at 60. So I'm going to click on this button that says percent transmittance in the top row. I'm going to click on display limits, and I'm going to set my start, instead of at 65, to say 58. Right? So I'm starting at 58 and going to 100. So now my peak is no longer going off scale. So next thing I want to do is label peaks, and up next to the baseline correct label, there is a find peaks button. If I hover over that, it'll tell me that's find peaks, and I'm going to click that. And it will set a horizontal gray line, and any peak that extends down below that horizontal gray line will be labeled. I know I want these 4 peaks, so I'm going to move that gray line by clicking here, right? And now it's going to pick up all of those. It's picking up a lot of peaks in this region, probably including some that we don't need, but that's a reasonable place to put my threshold. And now I'm going to click replace again, and so now I've got a new spectrum that has some peak labels in it. Now time to save this as a different name, like DCL-42B-1 corrected, so that I don't accidentally delete my original spectrum in case I need to work with that in the future. And I have to tell it where to put that, because by default it's going to a folder called OChem. So it's labeled peaks that I want, but it hasn't labeled all the peaks that I want. In particular, it hasn't labeled this small peak here on the side of the 2849 peak. By using the annotation tool, I can actually drag those peak labels so they're conveniently different from each other. And I can get it to select peaks that it didn't otherwise select. By holding the Shift key down and clicking on that peak, I can get it to find the center of that peak and actually label it. If you make a mistake, you can simply hit the backspace key and enter, and it will make the peak go away. Right, so the annotation tool can allow you to move that peak label somewhere convenient, and just hitting return will get you back out. So I've got a peak at 1736, I've got a nice strong peak here at 1472. I know that's a relevant peak. This peak at 1417 is probably not important, so I can click on it and delete it and make it go away. The 1391 peak is important. And then the 1179 peak looks like it's probably important. Some of these other peaks are likely to be less important, right? Especially these really small ones. So I can delete the small peaks that I really don't want to see. Clean it up significantly. So I've got a series of peaks in that region. I've got an 1113 peak that's significant. This 1095 is probably not. And this 717 peak turns out to be quite important. And then by going back to the select tool, I can prevent myself from accidentally labeling background. So we'll save that. So that's one of the things you always want to do when you take an infrared spectrum, is you want to correct your baseline, and then you want to label your peaks and print a copy as a PDF file. Which is what you'll be uploading. Change the name from trimeristin uncorrected to trimeristin correct, and that'll be available to you on Blackboard. So it would be nice if we knew what these peaks were doing there, why these individual peaks are there, what functional group is responsible for them. And there are two things up here in the far right. You see there's a button that says Library Setup, a Library Manager, and a Library Search. And then there's a thing that looks like a glass that says IR Spec. That IR Spec button is the one that will look for what functional groups it thinks are present in the molecule and tell you which peaks are from those functional groups and what individual bond vibration is causing it. So I can go to the Library Setup. And I have two libraries, the Georgia State Crime Lab Sample Library and the Nicolay Condensed Phase Academic Sampler. Trimeristin, turns out, is not in either of those libraries, but there are probably some compounds that are similar to trimeristin in there. So then I can click on the search button, and what it will do is it will pull up the best two closest to the match, and then down here it'll give me a list of 5 compounds. So you'll see that the match is 46.54%, similar to isobutyl formate, 45.59 to ethyl butyrate, 42.76 to butyl formate, and those are the purities of the sample. The 98% is the purity of the isobutyl formate. None of those matches are particularly strong, but comfortingly they're all esters, and we know that our compound is an ester. So that's a good sign. At least we have functional groups that are consistent with an ester. We're going to want to print that search result, and some of the compounds that you're in the lab will actually have matches. And we want the search result spectra and the list of matches, and I like to print those on separate pages. So we can click the button that says print on separate pages and OK that. And we can call that trimeristin search. So we now have a PDF file that has the search results in it. We can close that window. The small gray X will allow us to close the search window and get back to the original spectrum. So we've searched and confirmed that it's probably an ester, although the individual ester that we know we have, which is trimeristin, is not in the library. And then we want to go to this IR Spec here and click on that, and it's going to tell us what it thinks is present. Specifically, it's going to tell us that it thinks that it's an aliphatic acetate ester. Well, it's not an acetate ester, it's a myristate ester, but an aliphatic ester. Aliphatic means not aromatic. It means there are no benzene rings present, as trimeristin doesn't have any, and it thinks it's an aliphatic hydrocarbon, and we do have long hydrocarbon chains. If you look up in the top left here, aliphatic acetate esters are in purple and aliphatic hydrocarbons are green. So this peak at 1700 or so is part of the ester. And these peaks in this region between 1000 and about 1300, 1300, those are from the ester, whereas these peaks in the 1400 and 1300 region, and these peaks up around 2900, and this peak at 700, those are there because of the aliphatic hydrocarbon. So we can print this search result. And we can save that as trimeristin functional groups or trimeristin interpretation, anything that works. And so now we can take the trimeristin corrected, the trimeristin search, and the trimeristin interpretation and combine those into a single PDF file, which is what you would normally upload. We'd like to know why those peaks are singled out, though. What is it about this peak in this 2900 region? What feature of an aliphatic hydrocarbon is causing those peaks to be there? What function of the ester is causing peak to be here at around the 1730-ish range? And the secret to that is these little eyeglasses under the info section. So we can click here on the eyeglasses for aliphatic acetate esters, and it will open a window that tells us about aliphatic ester groups. It'll tell us how to name them. So this is methyl caproate or methyl hexanoate. Hexanoic acid has a common name of caproic acid, which comes from goat, caper. There's capric, caproic, and caprylic acid, which are 8, 10, and 12 carbons, respectively, I think, that all come from goat and are distinctively part of the odor of wet goats. And then we see down here the spectral interpretation. If we scroll down, it will tell us that that region around 1735 is typical of the carbon-oxygen double bond stretch. We have a saturated ester. Right? Saturated hydrocarbon means no double bonds, so we would expect to see a peak somewhere between 1730 and 1750 for a carbon-oxygen double bond stretch. An unsaturated ester would be a slightly different location, a little closer to 1700, and then a vinyl group is a CC double bond, or an alpha keto ester. We don't have to worry about those. So we know that that peak in that 1735 is present because of a carbon-oxygen double bond stretch, which is a functional group that we have in our ester, right? Ours doesn't look quite like this. Ours has a 12 carbon, or 13 carbon chain rather here, plus the carbonyl, which is 14, and not a CH3. Ours has a glycerol there, but it's still an ester. And it will also tell us that the peaks in that region between 1000 and 1200 are probably from a carbon-oxygen double bond stretch. What's listed is a formate ester, an acetate ester, a phenolic acetate, and an acrylate. We don't have any of those functional groups. Right? We don't have an acetate, we have a myristate. We don't have a formate, that's an ester of formic acid. We don't have any phenols, and an acrylate has a CC double bond in it. But we know that those peaks around 1200 in our spectrum are probably due to a carbon-oxygen stretch. It's actually common on an ester group to have two different carbon-oxygen single bond stretches, because you'll notice that we have a carbon-oxygen single bond stretch from the carbonyl, right? That's an sp2 carbon to oxygen, and we also have it from the aliphatic hydrocarbon from the sp3 carbon to the oxygen. Because the sp2 CO bond is a little shorter and stronger than the sp3 CO bond, you might expect to see those in two different locations, and you do. The 1235 peak is the sp2 CO stretch, but you also see this peak here, a little less and closer to 1000, and that would be the sp3 CO stretch. And we'll see both of those in our spectrum as well. So we know that the main two peaks that we're going to be seeing in our for the aliphatic esters are the peak up at around 17-ish or 1740, and then the carbon-oxygen stretches. You'll see here that this is an acrylic ester. Right? It has a CC double bond here, in addition to the carbon-oxygen double bond, and so the CO stretch is in a different location at 1190. Right? That CO stretch now takes a little less energy because there's some resonance that weakens that bond a bit. But that's not relevant for us. We have a plain old aliphatic ester. We would expect to see about the same place as for propyl acetate, somewhere around 1235 for the carbon-oxygen sp2 single bond stretch, and somewhere around 1745 for the carbon-oxygen double bond stretch. So if we go to our original window that shows our spectrum, we can identify this peak at 1736. That's the carbon-oxygen double bond stretch, and then we can see this strong peak here at 1179, and this peak at 1113. Those two are almost certainly both carbon-oxygen single bond stretches, probably the sp3 CO stretch here at 1113, and the sp2 CO stretch here at 1179. Right. These other peaks in the 1274 region, they're a little less intense. The bigger the dipole moment for the bond, the more intense the peak is, because one of the rules for IR absorption is that it has to change the dipole of the molecule as well as having energy. So we've got our carbon-oxygen single and double bond stretches. We can go back to the window for spectral interpretation, and we can click on the spyglasses for the aliphatic hydrocarbons, and that will tell us that we should have CH3 and CH2 stretching absorptions, and we would expect the asymmetric stretching vibration somewhere between 2950 and 2975, right? And the symmetric between 2885 and 2865, and a little different for the CH2. It really wants me to make Firefox my default browser. So if you take a close-up here of hexane, which is a C6 hydrocarbon, you'll see that there's a peak listed at 2860, which is from a symmetric CH2 vibration. That's the two hydrogens lengthening and then shortening at the same time, both hydrogens going further away from the carbon and then both hydrogens coming closer. And at 2874, we expect to see a symmetric CH3. You'll notice that that peak was weaker in our spectrum because we have far fewer CH3s versus CH2s in our molecule. This is unfortunately a typo. This 2826 is obviously not right. That should be 2926, because if it were 2826, it would be over here. Right? So at 2926, we see the symmetric CH2, and at 2959, we see the asymmetric CH3. That's for one hydrogen getting closer to carbon while the other gets further away, and then the opposite direction. So out of phase as opposed to in phase for the asymmetric stretching. So we have four different peaks because we have symmetric and asymmetric stretching for the CH2s in our molecule and for the CH3s. And usually you don't see clear delineation of those. You just see a lot of peaks between about 2850 and 2970, and you know that's an sp3 carbon-hydrogen stretch. Most molecules have it. In the region around 1450 to 1470 and 1379, we see a strong CH2 scissor. Right? We got a lot of CH2 groups in our molecule, so we would expect to see a pretty strong CH2 scissor vibration, and then there's a symmetric CH rocking vibration at about 1379. We have 3 CH3 groups, so we should see a fairly weak peak at 1379, but we've got a large number. We've got 36 CH2 groups, so we should see a very strong CH2 scissor. We're probably not seeing this asymmetric CH3 vibration, rocking vibration, sorry, not wagging vibration, because the CH2 scissor is so much stronger. So we know that the peak at 1470-ish is a CH2 scissor, and the one at 1380-ish is a CH3 rocking vibration. And if you had branching, right, you might see more than one peak in that 1380 range, right? Because now we have 2 CH3 groups attached to this carbon and 1 CH3 group attached to that carbon. But we're not seeing that, right? Because we have only single CH3s. And then if we go down a little further to the bottom, you can see that there's a CH2N rocking absorption in that region between 700 and 750. When there are 4 or more CH2 in a row, we often find a rocking vibration at 720 reciprocal centimeters, and if we have a very large number of methylene groups adjacent to each other, 10 or more, we do actually have 10 or more, but we're seeing just a single peak, not the double peak, if we go to a really large number of CH2s. That rocking vibration is the CH2 groups doing this, kind of going back and forth. So you've got your 2 CH2s adjacent to each other doing that. And if you've got a bunch of them in a row, you'll see that rocking vibration. So this enables us to identify some more peaks in our spectrum. If I close that spectral interpretation window, right, we know that these peaks in the 2850 to 2955 region are the symmetric and asymmetric CH2 and CH3 sp3 carbon-hydrogen stretches. This 1472 peak, that would be our CH2 scissor. The 1391 peak here is our methyl rock. And then the 717 peak, that's our CH2N rocking vibration, where n is greater than 4. In our case, n is 12. 12 adjacent CH2s in our 14 carbon chain for the myristate, causing a strong vibration there. So the peaks in the 2850 to 2950 region are carbon-hydrogen stretches from an sp3ch bond. 1736 here is a carbon-oxygen double bond stretch. 1472 is a CH2 scissor. 1391 is a CH3 rock. These peaks in this region from 1113 to 1274 are carbon-oxygen single bond stretches, the strongest being at 1179 and 1113. And then the peak at 717 is our CH2N rocking vibration. So the spectral interpretation guide, right, will enable us to find out things about our spectrum and gradually learn how to interpret IR as we take IR spectra throughout the semester.